Hello everyone, welcome back to the course. Up till the last class, we have tried to understand the economics behind production of hydrogen from fossil fuels, mainly natural gas and coal. We tried to understand how the economics works behind both the processes. We found that the processes state of the art, they have been used for almost a century now, and the economics is well settled, and this is where the economics for the future targets of green hydrogen production also come from. But one of the downside of producing hydrogen from fossil fuels is we are anyway releasing CO2 into the atmosphere. So if we are going towards the hydrogen economy with the sole aim of bringing down the global warming potential or the GHG emissions, possibly we cannot continue on producing hydrogen from fossil fuels. So in that case, we have two options. Either just capture the carbon which is coming out from this fossil fuel production pathways, or the other pathway is to adopt certain pathways which don't lead to emission of any CO2 as well. So let's discuss the first option now. What if I am producing hydrogen from fossil fuels, but in the aim of doing so, I am also capturing the CO2 that comes out of it. So we'll try to understand what are the possible avenues and how much does it cost to capture the CO2 that can come out from a fossil fuel based hydrogen pathway. So just to repeat, if I am producing hydrogen from fossil fuels, carbon is inevitably going to get emitted, and this carbon is going to come from two sources. So I would want you to recollect the discussion that we would have in the previous classes. So there are two major sources of CO2 in the conventional processes. So if I am talking about natural gas, the CO2 comes out as a flue gas. So the flue gas is basically coming from the fuel that I am going to burn outside the steam methane reformer for helping it reach the temperature of 850 degrees Celsius or so. Then another major source of carbon comes after the water gas shift reaction, where after all the carbon monoxide has been converted into carbon dioxide, and I would want to remove all the CO2 so that I can get a pure stream of hydrogen. And there could be different technologies which could be utilized for the removal of this CO2, but herein also I get a pure stream of CO2. But CO2 is not the only greenhouse gas, there are other gases as well. We also have gases like methane and N2O, which have a different potency as well. So do we have any emissions of this? Well, to some extent, yes. If I talk about methane, methane is normally found when I am using natural gas, it's nothing but methane. And the supply of this natural gas from the natural gas fields to the SMR reactors or the production facility for hydrogen could have significant fugitive emissions where the methane gets lost. So that needs to be accounted as well. Where is the N2O coming from? N2O basically comes from the high temperature combustion, which again is involved when we are burning gases outside the reformer. But as such, CO2 being the major gas, that will be a major concern. But it is also important to understand the processes that we are trying to understand also tend to have significant methane and N2O emissions. So trying to understand the methane emission, so we also need to first understand that it's not that 1 kg of methane if gets emitted would have the same effect of 1 kg of CO2, because the global warming potential is quite different for the two gases, and methane happens to be much more potent greenhouse gas as compared to CO2. As such, the effect is roughly 28 times as compared to that of CO2. So by that I mean, if 1 kg of methane is released to the atmosphere, the effect is almost equivalent to the release of 28 kgs of CO2 into the atmosphere. So by that, it's a much more potent greenhouse gas. And as such, methane emissions occur when I'm recovering natural gas from the natural gas deposits. It also tends to occur when I'm supplying natural gas in the form of pipelines and storing natural gas. It's also going to occur from the coal beds. So if I am using a coal-based process for production of hydrogen, methane is often associated in the coal beds, and normally it will be emitted if not captured for some other uses. So this methane normally goes to the atmosphere. And also if I am going towards the open cut mines, again the methane goes into the atmosphere. And these fugitive emissions need to be accounted for if I am going to produce hydrogen from coal. It's not that we can say that whatever is getting lost to the environment we are not concerned about, because if the mining of the coal with the sole purpose of hydrogen production is happening, these emissions have to be accounted in somewhere, because inevitably these are going to the atmosphere and are going to cause global warming. Another gas that is of concern is the NOx or the N2O to be specific. So if I talk about nitrous oxide, the global warming potential is even more severe, of the tune of 265 times, which means 1 kg of N2O if released to the atmosphere would have a similar effect as done by 265 kg of CO2 released to the atmosphere. But the good point here is that N2O is formed on a very small level, and it's one of the NOx that is produced. So NOx are basically produced when there is a high temperature combustion that is going to happen in the atmosphere. So NOx is basically formed when we have a high temperature combustion which involves nitrogen, and because of the high temperatures of around 850 degree plus that are common outside the steam methane reformer, NOx are formed. But the quantity as such is not very significant, but nonetheless they are formed and they end up in the atmosphere, which could have like problems of global warming. Further, we also need to understand in a conventional process which is based on natural gas, there would be two sources of carbon dioxide. One basically stems from the gases that is outside the steam methane reformer, which are quite dilute in nature. Why are they dilute in nature? Because what I am doing outside the reactor or the SMR, I am burning a fuel. In majority of the cases, this fuel is going to be natural gas. So whenever I am going to burn natural gas in the presence of air, which is going to be the normal oxidizing agent, the gases that are a result of it would have maximum amount of nitrogen. The amount of CO2 in that stream is roughly of the order of 10% or so. If that is the case, probably it's very difficult to capture. Then another major stream happens after the water gas shift reaction. After the water gas shift reaction, I would have some kind of carbon capture technique to come in, wherein I am capturing all the CO2, and that leaves me with almost pure stream of hydrogen. This stream is much more concentrated stream, easier to capture and easier to get sequestrated as well. Just to give you an example, so if I am talking about the dilute source, this is basically stemming from the fuel that is burning outside the steam methane reformer. So the typical gas that you would be having outside the reactor which is going to get burned would be a combination of methane, which is shown in grey here, and then the oxidizing agent would be air. It consists of 79% nitrogen and 21% oxygen. Also the gas could have some amount of CO2 in it. After the gas is burned outside the reactor, which is the sole aim of providing heat to the reactor, the output nitrogen remains as such. Some of it of course gets converted to NOx emission, but that's very less. Majority of the nitrogen escapes as nitrogen, and this is what you can see in the flue gas as well. Majority of the flue gas composition is made of the nitrogen content. Then we also have significant amount of water coming in. So where is this water coming in from? If we are consuming or we are reacting methane, which is having carbon and hydrogen molecules, the hydrogen molecules are going to react with oxygen to produce water. So this gas is going to have significant amount of water as well. So roughly around 10 to 15% of water in the gaseous form is also there. Then normally it's a methodology that we will be burning this fuel in the excessive supply of air, which means I will be providing much more air than what is stoichiometrically required. Why is that done? That is done basically to enhance the combustion, enhance the efficiency, and bring down the formation of particulate. And this is the reason why you find oxygen herein as well. So what is happening here is I am providing much more oxygen at the inlet as compared to what is needed stoichiometric. So even after the combustion is complete, all the methane that is present in the natural gas is converted into carbon dioxide. We will still have some oxygen remaining because that is in excess. And finally, the carbon inside methane is going to get converted into CO2. And as you can see, for a typical flue gas that is coming out from the combustion, this is of the order of roughly 10%. This is something you can expect from the flue gas. And as you would have imagined that it's going to be a difficult task to absorb CO2 with this concentration, because 90% of the gas is something that is of no use, and that is one of the reason that traditionally these gases are vented off to the atmosphere. So after you have some kind of cleansing mechanism for NOx as well as particulate, you would release this gas into the atmosphere because it doesn't make much of a sense to capture this CO2. But nonetheless, this CO2 is going to be significant. And as we have discussed in the previous classes as well, one way to avoid this gases altogether is go towards a methodology that is based upon partial oxidation. What is happening is partial oxidation is in the methane reformer, you are reacting the methane with oxygen, and it's an exothermic reaction occurring at around 1500 degrees Celsius. So that entails I do not need to burn a fuel outside the reactor, which is resulting in this flue gas. So I can altogether avoid the production of this fuel gas by adopting a process like partial oxidation. So companies like Shell have been adopting partial oxidation process because they would want to aim for blue hydrogen rather than green hydrogen, where they are capturing the CO2 that is coming from the hydrogen production. Then if I want to capture this gas that is being released at around 10% concentration, there is one methodology that is used at scale, and this is basically an absorber and a stripper that is using MEA as an absorbent. So basically what happens is you have a flue gas that enters. The typical concentration can change from 3% to 15% of CO2. So these kind of technologies basically has been formulated for capturing the flue gas that comes out from the thermal power stations, which might be either running on coal or natural gas. So if a thermal power station is running on coal, the concentration of CO2 is roughly of the order of 15%, and if the thermal power stations are running on natural gas, the normal CO2 concentration is around 3 to 5%, because natural gas tends to have much more carbon to hydrogen ratio as compared to coal. So the first thing that you would need to do is to cool this down, because these gases are coming out at elevated temperature, and they also tend to have a great deal of moisture, around 10% or around 15% water is already there. So you would want to remove this water before this enters into the absorber column. So what if the water enters into the absorber column? Nothing, it's going to dilute the absorbing liquid and bring down the efficacy. So it's always advised that I remove all of the moisture or as much as possible before you enter into absorber, and this can be done with the help of cooling water, but the cooling water that is used in this case is also significant. So once the flue gas enters into the absorber that has solutions like MEA, so when I say MEA, I am basically saying chemicals like methyl, ethanol, amines. So these are one of the traditional absorbing materials that are being used, but there are many additions that are available in the market today. So that absorber is going to selectively absorb much of the CO2 such that the lean gas that exists from the top would have less than 2% of the CO2 that is coming out. Now the CO2 rich absorbing liquid is going to get from the down of the absorber, get heated from an heat exchanger, then enter into a stripper column. So what happens in the stripper column? It's operating at a much higher temperature, roughly of the order of 110 to 120 degrees Celsius. If I compare that with the absorber, it's normally working at 45 degrees Celsius. So because of the high temperature, the absorber is going to release the CO2, and this CO2 can then be compressed and extracted as a relatively pure stream with more than 90 or 95% CO2 concentration. So this is how you would want to concentrate the CO2, and once the stream is available, you can use it for either sequestering or for utilization purposes. But where do you get the heat for this 150 degrees Celsius? So normally you would be raising steam, and this steam would be raised by using some kind of fuel, and traditionally this fuel has been some kind of fossil fuels. So to repeat again, even the capturing of the CO2 would have a good amount of energy utilization. You would be burning some kind of fuel for raising the steam and reaching temperatures of 150 degrees Celsius, and so you need to be careful while saying that if I am capturing CO2, it doesn't come at an expense. It does come at an expense in the form of I would be using much more fuel, and it's going to be expensive as well. And after the CO2 is released, the absorbing liquid can be recirculated back to the absorber, where it's cooled back and enters into the absorber. Then this is how the whole process looks like. If I would want to look at the economics of this whole process, let us try to have a look at it. So there are many proprietary chemicals that are available for such a thing. So there are 3 of them listed down. So one is the MEA by the Dow, then there's another MEA by another company. And if I'm looking at the carbon capture like rate of around 1.8 million tons a year, so that basically coincides with like what is the typical amount of CO2 that you would be getting in the flue gas for the typical capacity of plant that we are looking at. So the capacity that, if you remember, is around 373 kilotons a year. So this is what we are aiming for, and this is the quantum of CO2 that I will be releasing in terms of gases outside the reformer. And if I look at the capex of these technologies, that is again coming from the source which has been listed, it's normally of the order of $300 million or so. If I assume that this plant is going to take 2 years for construction, then 20 years of operation and 10% of discount rate and including a royalty of 2%. So possibly I would be using a 13.86 as a return on capital factor, and this brings the capex of roughly $40 million a year. There would be significant OPEX which would be used roughly of the order of $50 million a year. It would be required maintenance as well. But the major cost here is the utilities. So when I say utilities, it's basically the fuels and the water that I'm using. Of significant concern here is the water that would be used to cool the incoming flue gas, because these flue gases are coming at an elevated temperature. I need to cool it down so that the majority of the water gets condensed, and this entails a good use of utility. And then if I look at the cost of carbon capture, this is normally of the order of $100 a ton. So that's pretty significant. So roughly $100 is something that I would be spending for capturing 1 ton of carbon, and that's pretty significant, and it's slightly on a higher end. And this is one of the reasons why like these kind of technologies have not been used very widely. One thing is that it's costly. The other thing is like even if you are able to capture it, what are you going to do with the quantum of the CO2 that is getting produced? So there are not much end uses. And just to make point, this is just the cost of capture. In case you would want to sequester it and put it in some kind of reservoirs, that cost would be an add-on to this. Then the second major source of CO2 would be from a concentrated relatively pure stream. And this is going to be the case if I am using coal based hydrogen production, where like majority of the CO2 gets released beyond the water gas shift, or in the case if I am using a partial oxidation reaction, where again this type of carbon capture is going to happen after the water gas shift. Now given that the concentration of CO2 in these gases is quite high and the pressure is also on the higher end, there would be many technologies would be available. And another thing that should be kept in mind is normally in these gases I would not be capturing CO2 alone, but along with hydrogen sulfide, and that is why the technologies would also called as acid gas plants or acid gas removal, because I will be removing significant amount of hydrogen sulfide as well here. But as such, since the concentration is quite high, roughly of the order of 30% or more, the technology is quite convenient and I can expect it to be quite economical as well. But I need to understand that there would be great deal of compression needed after the capture is done as well. So just to give you an example, the technology is available. So as compared to the earlier case where I would basically rely on the methyl ethanolamine, I could have different ways of technologies. So here you see a great deal of absorbing agents like diethanolamine, Benfield solvent, which is nothing but potassium carbonate solution and had been used at significantly in the ammonia industry for capturing of the CO2. Then we have adsorbents like Selexol or triethanolamine. So these all are the technologies which are absorption based. Then there could be membrane based technologies as well. So when I say membrane based technologies, I am looking towards membrane which are selective to the passage of carbon dioxide. So what is happening is whenever we are having high pressure gas coming in, the membranes are selective to the passage of CO2 such that it passes the membrane and goes towards the low pressure side, and a concentrated stream of CO2 could be produced, whereas on the high pressure side you would have a CO2 depleted gas that is available. Another technology that would be of concern is the cryogenic technology, where I am basically bringing down temperature of the gas such that majority of the CO2 is going to condense. So it's basically using the Joule-Thomsol principle, where I am basically compressing the gas and then expanding it again and again such that the CO2 is going to condense and is removed from the solution. Again, let us try to look at the economics, how that looks like. So if I am talking about a conventional plant which would be having roughly 1.6 or 1.7 million tons of CO2 in the gas that is coming in, the capex for these technologies could vary somewhere between 150 to 300 million dollars. And again, if I would have to calculate the return on capital, that is similar to the earlier case, wherein I would have 2 years of construction, 20 years of operation and 10% as the discount rate, I would see that there is a significant capital charge. And then comes the operating expense, maintenance expense, but again utilities are quite significant here again. So by utilities I mean the energy or the water that would be needed for the capturing process. And if I talk about the total cost in terms of dollars per tons of CO2 equivalent, I can see there could be a couple of technologies that are in the range of roughly $50 of carbon capture price per ton. So this is much more better. and it tends to be much more nearer to the carbon price that we have in the market, and that's again a variable commodity, but much better than capturing CO2 from the flue gas. And this is one of the reasons that majority of the places it would be advisable to capture the CO2 directly from a more concentrated stream where the CO2 concentration is more than 30% and the pressure is normally greater than 10 bars or so, which is normal for a high pressure hydrogen or ammonia plant. Further, we also need to understand that normally now what are you going to do with the CO2 that you have captured? Of course, capturing the CO2 is good. The hydrogen that is getting produced anyway had to be stripped of the CO2 stream. But once you have captured the CO2, what do you do with it? Now, people are of the opinion is like put it through pipelines and then shift it to some kind of underground reservoir where it is going to stay for quite some time, and that is going to have expense as well. So, if I am talking about the piping expense, the normal rule of thumb is that like if I am transporting CO2 for a 1 kilometer, the construction expense alone is going to be of the order of $1 million, which is huge. And not so good condition arises because of the availability of such sites. So, if I talk about India, like we have not been equally working towards carbon sequestration and storage, because one thing is that we do not have many like crude or coal producing facilities. Another thing is in the past we have not seen much value into it. So, if I talk about India, there is just one experimental site in Vindhyachal that is operated by NTPC, where some kind of carbon storage and utilization is being explored. So, if I would have to still capture the CO2, what are the available options that I can take advantage of and put the CO2 somewhere? So, the first option that comes is put it into the deep coal beds, which are basically no more into utilization. So, these are the places where coal would have been extracted in the past, but it is no more usable currently. And so normally I would have to like pressurize the gas up to 8 to 10 megapascal, which is basically 80 to 100 bars, and put it into the coal seam. And it is expected that the CO2 is going to get absorbed on the coal surface and it's going to remain there for quite some time. Another option that has been proposed is that of enhanced oil recovery. So in enhanced oil recovery, I can basically economically use carbon dioxide. So this is a technology that is much in use in North America, where they are using a concentrated CO2 as a dense phase, where they are pumping the CO2 into the oil seams. So because of the highly pressurized CO2 getting pumped in, it basically enhances the fuel production from these fields. So although the CO2 is getting sequestrated, it is also helping the companies increase their oil production and make up for the revenue. And this is one of the areas where majority of the carbon sequestration or carbon storage have been utilized in the US or other parts of the developed world, because this was helping companies increase their oil production and increase their profit margin. So it was not always because of the environmental concerns, but with the aim of increasing the oil production. And normally you would compress the CO2 streams to roughly 150 bars in this case. Another pathway that has been proposed is the disposal of the CO2 into some kind of saline aquifers, which would be somewhat below the depleted oil and gas reservoirs. So there could be some saline formations where you can just put in CO2 and hope that it's going to remain there for quite some time and doesn't leak back into the water tables and contaminate it. Further, the pressure that would be needed in these kinds of technologies would be even more, roughly of the order of 150 to 180 bar. But there is always a danger of CO2 coming out and causing other different issues in this case. People have also been advocating the use of abandoned oil and gas wells for basically storage of CO2, and again you need a similar pressure for pumping in CO2 at this case as well. But they also need to be understood, like if there could be some kind of issues which can lead to future earthquakes or other geological issues which need to be taken into account. So if you have abundant coal and gas wells where you don't need to extract much oil, these could be the probable sites where you can put in more amount of CO2. And finally, there is a whole bunch of people who would want the CO2 to be just dumped into the atmosphere at the depths of more than 1 kilometer in depth. So it's expected that the CO2, when it's pumped down, is going to form different kinds of carbonates. But there is also a fear that this might basically change the acidity of the ocean, which could have drastic effect on the aquatic life. And also, according to the London Convention, it is prohibited to basically store any of the industrial waste into the oceans. So you cannot dump any industrial waste into the ocean as per the international convention. And if you are dumping in CO2 into the oceans, possibly that's also treated as a waste. And further, if I talk about the energy that would be required, that would be of the turn of 300 bars or so. So these are the ways in which I might be able to store the CO2 that I am producing from these hydrogen plants. But there is also some people who said, why not we utilize CO2? A major way we are utilizing CO2 is that in terms of the carbonated drinks that we are so used to drinking. So although all of these have some amount of CO2 that is getting absorbed in it, so why not just put a CO2 into this? And then there could be other applications of CO2 in the industry which could be used as dry ice and other chemicals as well. But just to set things into perspective, if I would have to say the global market of CO2 is roughly of the order of 0.14 million tons a day, whereas the production globally from different sources is 104 million tons a day. So there is a huge mismatch between the production and the supply of carbon dioxide. The need of carbon dioxide happens to be 5 orders of magnitude lesser than what we are emitting currently, and this is going to be true for the case of hydrogen based CO2 production as well if it is coming from fossil fuels. Then there might also be a case for a greenfield geo-sequestration site, wherein like we would want to put up and explore a new site where the hydrogen plant is expected to come up. Again, that's a good option, but we also need to be careful about like doing the seismic studies around that place, because it might not be causing some geological phenomena which we are worried about later on. But again, this is something that is not explored on a very vast level. People have always tried to basically go with the sites which are empty coal or oil seams which are no longer usable. Another major problem that is going to occur with the geosequestration is that if I am able to have a hydrogen plant that is going to operate for a couple of years. So normally I would assume that such a plant is going to operate for 20 to 30 years, whereas the sites that I might be able to locate for carbon sequestration are going to be mainly static in site. So how do you reconcile the two things? One is the continuous production of hydrogen, and then the second is the site that I am going to get might not be able to reserve all the CO2 for the lifetime of the plant. Further, it is also expected that as time progresses, the voids are going to fill up with gases and there is going to be an increased resistance to injection that is going to happen. Further, we also need to be pretty sure that the CO2 is going to remain there for a quite long time, roughly 100 years or more, and also be careful that any carbonic acids or carbon based chemicals that are being formed does not basically leak out and cause other problems in the water table. Just to give you an example about the past CCS facilities, so here is a list of some of the major CCS facilities that has been operating in the past, and you would find that like these kind of things have been operating from way back in the 1970s. So just try to recollect, back in 1970s we did not had much of the CO2 problem. No one was talking about it, or they were even aware of it, but still we were having carbon sequestration happening, and the aim was enhanced oil recovery. So this is not a new technology that we are talking about. People have been capturing and sequestrating CO2 for quite some time, and you would notice that majority of these locations or these carbon sequestration facilities tend to be in the developed world. The US, the Europe are the major places. And further, it's also worthwhile to look at the capacity. Most of them are having a capacity of roughly 1 million tons of year of the sequestration capacity. Further, some of the new CO2 capturing facilities can be seen here. Again, majority of these are aimed for enhanced oil recovery, and again majority of them are coming in countries like US. Again, to repeat, in India, its potential of carbon capture and storage has not been explored much, and there is only one operational plant, that's a pilot plant that's operated by NTPC in Vindhyachal. Coming to some of the nice examples for carbon capture and sequestration, so one of the closest examples that comes in the case of blue hydrogen or hydrogen production from coal would be the Dakota Gasification Company that has been operating since the 1980s, where they are using roughly 6 million tons of lignite, which is a grade of coal, in the Roorkee gasifiers and producing a synthesis gas, and they are also capturing the CO2, which is of the order of 2.5 to 3 million tons every single year, and this gas is basically supplied to the neighboring country of Canada, where it is used for enhanced oil recovery in the Weyburn field. So basically, it's the economics that has been making this thing work. They found economic use of this carbon dioxide that is getting captured, and that is helping them increase their oil production. And this is one of the facility that is available and that has been operating for quite some time. Another facility that has been operating quite successfully is the Sleipner gas well near the coast of Norway. So wherein they are extracting the natural gas from the underground reservoir, but this natural gas reservoir also tend to have significant amount of CO2. So what they are doing is they are capturing the CO2 from natural gas in the offshore location as well, and then storing the CO2 again in some kind of formation which is called the Utsira basin, and this plant again has been operating for more than 20 years or so now. So, it is one of the successful stories as well as offshore carbon capture is concerned. So, these kinds of plants have been operating in the past and have been operating quite successfully, and it is also hoped that there could be a nice amalgamation of this technology with the future production of blue hydrogen, where we are using fossil fuels for production of hydrogen, but we are capturing majority of the CO2 that results from these efforts. It is also pertinent to understand some of the limitations that might come up from this kind of methodology. So, for this let us try to understand this with the help of a question. Now, suppose I have this 373 kilotons of hydrogen production that is happening from a hydrogen plant, and that is happening through natural gas. Now, suppose I am using natural gas, which means there would be significant amount of CO2, both concentrated and dilute form. So, if I would want to capture all of this CO2 that is coming out, and that the number is going to be roughly around 3.9 million tons of CO2 every single year, and my aim here is to capture 90% of the CO2 and store it in some kind of reservoir. The aim here is the time that it will be required for a typical reservoir to get filled. So, I am looking at a typical hydrogen based facility which is producing blue hydrogen using natural gas. This is the amount of CO2 that would be emitted. My aim here is to capture 90% of the CO2, and this capturing of the CO2, if I would have to sequester in a site or in an empty oil field which has a volume of 0.5 billion barrel. So, when I say 1 barrel, it is roughly equal to 159 liters, and that is a standard unit for denoting the volume for crude purchase as well as for storing of the CO2. Further, we also need to understand when we are storing CO2 in these kind of formation, it has to be at supercritical conditions, which is normally 80 degrees Celsius or more, and a pressure beyond 700 bars. And at these supercritical conditions, the density of the CO2 that we are going to generate is going to be quite high, roughly of the order of 860 kgs per meter cube. So, let us try to briefly understand or solve this question together. So, the hydrogen that I am planning to produce is roughly of the order of 374.6 kilotons a year. The CO2 that comes out from this exercise would be roughly 3.95 million tons per year. Now, if I would have to capture CO2 and I would have to then change or convert it into volume as well, given the supercritical density of 860 kgs per meter cube. So, the CO2 that I would aim to capture would roughly be of the order of 4.14 into 10 to the power 6 meter cube or million meter cube. So, just remember here I am capturing just 90% of this 3.95 million tons, and this million tons I have also converted into the volume basis using a density of 860 kgs per meter cube. Further, if I talk about the field capacity that I would have in terms of 0.5 billion barrel, the field capacity of 0.5 billion barrel, if I convert that into meter cube, would come out to be 79.5 into 10 to the power 6 meter cube. If I divide this field capacity with the CO2 capture, and this CO2 capture rate is an yearly value. So, this is the amount of CO2 capture that I would want to happen every year, whereas the field capacity is something that is static. The years it will be required, or the times it will be required to fill the reservoir would roughly be of the order of 19.2 years. So, it will require only 19 years or so to fill in this reservoir. So, this is the problem that you are normally going to face in terms of carbon sequestration, that even if you happen to have a nice empty reservoir where you can sequester the CO2, it is going to fill up rather fast, and the size of the reservoir that I have assumed in here is quite significant, and that is going to fill up in roughly 19.2 years. And if I would want to operate my plant for maybe 30 years or 40 years, as is the case for coal based power plants, I would have to come up with more fields, which is finding them which might not be as easy as possible. Another thing that we need to be understanding is like the production of hydrogen is going to grow significantly over the years. So, here is this one projection that is given by Statista, and it says that by the year 2050, if the current policies are taken into account, the hydrogen production might be of the order of 287 million tons per year. So, let us take this value or so and then try to estimate that if this was the hydrogen production maybe 25 years from now, what would be the number of sequestration sites required if I am assuming that I will be using whole of blue hydrogen. So, the question that I am trying to address here is, let us assume that I am 25 years into the future. The current hydrogen production is 287 million tons, and globally we have had a consensus that I am going only for blue hydrogen production, which means I am only going to produce hydrogen from fossil fuels and capture all of the CO2. So, in this case I am aiming for capturing 80% of the CO2 that entails, and the empty oil field or reservoir that is available, the average volume is roughly of the order of 100 million barrels. Just remember, in the last example the volume was 0.5 billion barrels, so it was 5 times this capacity. So, my aim here is to estimate the number of oil fields that would be needed if I would have to capture the 80% of the CO2 that entails from this particular avenue. So, if I would have to solve this, let us do some back of the envelope calculation. The hydrogen production that I am aiming for is equivalent to 287 million tons a year. The CO2 production that would entail, again this would be a function of the technology utilized. I am just taking one of the average value that is coming from one source. If you are referring to some other source, this CO2 value could be different as well, and this would be of the order of 3032 million tons a year. And if I would have to capture the CO2, so I am capturing 80% of the CO2, and again this CO2 is converted with the help of the supercritical density, this would be of the order of 2821 million meter cube per year. So, this is the amount of CO2 that I would have to capture per year, roughly 2821 million meter cube of CO2. The capacity of the field, or the average field capacity, is roughly of the order of 15.9 million meter cube. And if I would have to estimate the number of fields required, this would be of the order of around 177. So, I would require roughly 177 empty oil fields, which might not be a very likely thing to happen, and this is something that I would have to keep on increasing, because that is not a static value. I would be keep on producing hydrogen year after year. So, just some observations from the current lecture. One thing is that if I would have to capture the carbon dioxide from the flue gases that is resulting from the steam methane reforming, the average cost is going to be roughly $100 a ton, which is going to be quite expensive. Whereas, if I am going to capture CO2 from a concentrated stream beyond the water gas shift, the cost can come down to roughly $50 a ton, which could be coming from different technologies. So, it is much more probable that if I am going for blue hydrogen, I will be capturing a much more concentrated stream, and I might be going for partial oxidation type processes. But further, there would be significant cost that would be added for the production of blue hydrogen, economics of which we will be discussing in the future classes. With this, we end the current class. Thank you.